Okay. All right. A simulation was conducted using 20 fair coins, where faces are heads and tails. All 20 coins were flipped, and the proportion of heads facing up was recorded. The process was repeated 40 times. Which of the following best describes the distribution being simulated? So, you have two choices. Is this a sample mean or a sample proportion? So we're talking about we're talking about we're recording what and actually it tells us right about the gate, the proportion of heads. So that means we get to rule out C, D, and E. Because C, D, and E refer to a sample mean. Okay. Now I'm just looking at this going, I disagree with my key. I'm trying to figure out what I was thinking when I circled the answer that I did. Because it says this process was repeated 40 times. A simulation was conducted using 20 fair coins where all 20 coins were flipped. So my sample size is going to be 20. Or is my sample size 40? I'm pretty sure. I mean, and again, I guess it depends what we're measuring here. I have my notes 0.5 times 0.5 divided by 20. So somewhere in my notes, I determined this morning I want to think my sample size is 40. However, in my notes, I have this is my answer and a sample size of 20. So I'm trying to figure out what I was thinking when I wrote the key last year, or whether am I off sorts this year or last year. Okay. I'm gonna roll with this answer because I'm pretty sure I was looking off the correct thing. So, okay. All right, I'll try to shut up on this one. I'll read it. The above display two sampling distributions, A and B, from the sample population, but with different sample sizes, which the following statements must be true about the samples. All right, the samples from distribution A do not appear to be random. I mean, the peak of that has nothing to do with random, so we'll strike out A. Sample sizes, I'm going to go down to the bottom just because I want to talk about all the bad ones first. The sample sizes do not affect the sampling distributions. Well, that's wrong because we know the larger the sample, the less the variability. And hopefully that's the logic to use to find the right answer. Well, which sample size is greater cannot be determined from these graphs. And again, we know that as sample size increases, so does the variability. The sample size of grade B is greater than A, and then A is greater than B. Well, because sample size increases, variability decreases. So that means B is my answer. All right, a lot of reading. I'll try to wait again. A survey originally consists of a simple random sample of size n from a population. The researcher obtains a grant to allow for a sample that is 4 times as large as the initial survey from the same population. How would the standard deviation of the original sampling distribution be related to the standard deviation of my new sampling distribution with the increased sample size? So again, they didn't come out and give us hard numbers, but we'll just talk about the answer straight up. We have 2 different ways to calculate a standard deviation of a mean or a standard deviation of a proportion. If I talk about the standard deviation of mean, we're going to take this, and we decided it's the square root of n, but we decided to make n 4 times as large. So if we simplify that a little bit, we can go with the standard deviation is going to be 2 times the square root of n. So there's my original sampling distribution, standard deviation, and then it looks like I'm going to be dividing it by 2, so it would be half as large. Okay, so that means that it's going to be answer C. If we were working with a proportion instead, again, it didn't tell me which, but as I said, it ends up being the same thing. P times 1 minus P divided by 4 times N, again, is that standard deviation. Well, all of this can remain the same as far as I can't do anything with P times 1 minus P. Wow. However, I can take the square root of 4 and we'll pull that out as a 2, and then we'll have the n over, and again, I'm left with half as much. So it didn't matter whether I was dealing with a mean or a proportion, it was still going to be half as much. Okay. 4. There were 6,218 insurance claims in a southern county following a recent hurricane. The distribution of the claims is strongly skewed to the right, with a mean of 137 and a standard deviation of 46. If all possible samples of size 80 are drawn from the population and a mean computed for each of these samples, which the following describes the sampling distribution. So again, we're describing, have to remember what we're describing here. The sampling distribution of size 80. All right, so we got means of 137, 462 all the way down there. So we know it's going to have that mean. It looks like we got some standard deviation calculation to do. However, we know because of the central limit theorem, the sampling distribution will be approximately normal. If sample size sufficiently large. Okay. And again, we have a cutoff for that. That would be 30. So size 80 is good. So we can eliminate B and A because they talk about a strongly skewed. So we're talking about these 3 at the bottom. And now it's just time to figure out what's my standard deviation going to be. The standard deviation of X bar. Again, this is you knowing where to find the equation. If you just know the equation, your comfortability with the equation, we know it's a mean. So we know that the sampling distribution standard deviation is going to be my population standard deviation divided by the square root of n. Okay, and either A, you got to know where to look for it, or B, just know it. Okay, so we know in this case we have 46,520 that we're going to divide by the square root of 80. So we end up with, I don't know, some number. Looks like I have E circled. The employee incomes in a certain large company have a normal distribution with a mean of 40,000, a standard deviation of 6,000. 9 employees are selected at random from this population. What is the probability that their average income is 44,000? Okay. Now I mean, if we're really the first thing that 9 employees are selected, so that's usually a thing of, hey, be careful here. My sample size is small. However, what about this problem allows us to keep going? My original population is approximately normal, so everything is good. So again, this is um, if I'm working the test, I definitely need to be familiar with my normal CDF because I'm probably going to do a multiple choice question like that. I prefer the writing. I mean, I love the fact that everybody uses their equations on the free response because I think that says more to the grader. However, in a multiple choice problem, knowing your CDF is going to be something to help it probably go faster because you really don't have to write this out, but it's a normal CDF. 44, we want to know what's the probability it is above 44,000. So 44,000 is my left boundary. 1E99 is going to be my right boundary. The mean income is 40,000. And this is just where you have to remember, we're talking about a sample of size 9. So I'm going to take my standard deviation, which is 6,000, and divide that by the square root of 9. Okay, so this is what you have to remember. Okay, it is a sample. It forces my standard deviation to change. Okay. Alrighty. Well, that's that document. And I said we had another document to work on today. Here we go. Actually, let's come up here and sampling district key return. We'll upload this to OneDrive. Not in chapter 3. Sorry, I should actually do this later, but I just want to. So you can go ahead and get out the. We're going to walk through the review together. So go ahead and work on number 1 and 2 because they're similar style questions. And then I'm going to go save this document where it needs to be saved, and then we'll come in and start working on that review. So taxi fares are normally distributed with a mean of 22.27, a standard deviation of $2.20, which should have a greater probability of falling between 20 and 24. The mean of 10 random taxi fares or the amount of a single fare and why. So again, this is probably your ability to drop in a 10-cent word. Okay, so this is all about the central limit theorem, and we can abbreviate that. It's a common abbreviation, so it's fine. The CLT, central limit theorem. Tells us the larger the sample size, the smaller the variation. A sample of size 10 is more likely to be near the middle than a sample of 1. And again, so the smaller my sample size, the more my really strange outlier is going to play into that. So if I have a really long taxi ride, or a really short taxi ride, that's going to cause that mean of my sample to be off. The more numbers, the more. If I only have 1 in my sample size, that one event is going to it could be really large or really small. Just like when we did my age in a sample, my age is going to cause an average age of a sample to go really high. But the more people we add to it, the more that kind of buffers it and brings that back to the middle. So now we want a mean of $24. So again, we're going to using the same logic as A. There is a greater chance of having an unusually large or small sample mean when sample size is small. I suppose we need to answer that somewhere. A single taxi fare. Okay, 2. Again, I'll try to do some. I mean, again, I have no idea what we're doing, what you're doing. You could be sitting there eating breakfast, watching cartoons for all I know. Not that you guys would do that. But hopefully we'll work on the review. Number 2. Suppose Pepsi claims that its production process is normally distributed and yields bottles with a mean of 157 pounds per square inch and a standard deviation of 3. As part of its vendor's surveillance. Surveillance? Okay. Pepsi strikes an agreement with the vendor that permits the bottler to sample the vendor's production to verify the vendor's claim. So suppose we select a random bottle, 1 bottle. What do the mean of the standard deviation? So because this is 1 individual, I mean, yes, we could consider it a sample of 1, but my formula is to divide by the square root of n, so the square root of 1 is 1, so it really has no impact. So I'm going to expect my sample to roll in at 157. My standard deviation rolls in at 3. What is the probability that that PSI, that single bottle, is less than 157? And again, there isn't much space here, but if we were to write out everything that we'd need, this is the probability of X being less than what? 155.7. We need to make sure we draw a picture. Again, you could use your normal CDF if you want. I doubt I write that in here. Okay, and again, the left-hand tail means we don't have to subtract from 1, so that was it. There was done. There was this was a Unit 1B problem. So here's about the whole part about the unit they were try to start grasping. In part C, now we're going to randomly select 40 bottles from the last production of bottles. What is the mean and the standard deviation of the sampling distribution? So now again, we're talking about that sample of 40. We have a sampling distribution. So now we're going to adjust the mean and standard deviation. So we know that n is equal to 40. It didn't ask me that, but it's always good to write down, I suppose. The central limit theorem tells us, again, we're talking about the mean of the sampling distribution because we have the mean of x bar down there. Same way over here, we have the standard deviation of x bar. So that indicates that we're talking about the sampling distribution. Okay. The central limit theorem says that the means will be approximately equal. So that means that mean is not going to change. However, my standard deviation has to change, and that's the part that we have to start cluing in on. My standard deviation of a sample distribution has to change by dividing by the square root of my sample size, which was 40. So that means I have a new standard deviation of 4743. So in part D, what is the probability that sample mean? So this is all stays roughly the same, and I realize I probably did a disservice on notes because I think I just drew a line down here. My probability statement actually going to change a little bit here because my probability statement, even though it's still x is less than 155.7, we're not talking about x anymore. We're talking about x bar. So do note that change there. Okay. The picture stays the same, so I'm just going to draw a line down through there. Okay. Again, the calculation remains roughly the same. We're going to go with 155.7. Except my standard deviation changed. So this is 4743. So it's now, it moves from being just a small negative 0.43 standard deviations below the mean to now it's 2.74 standard deviations below the mean. So that's a long ways away, becoming very, very rare. So rare that it's like super small. All right, E, in order to reduce the standard deviation of 50 cent by half, what large, and I guess I should say reduce the population standard deviation. So that way we're clear, whether we're talking about the population or that previous sample. How large does sample size need to be? So this actually is going to be an extension problem. Nowhere in our notes have we talked about this, okay? But this is our ability to connect the dots as far as what we're talking about, the sample size of a mean, okay? So I know that the standard deviation of my sampling distribution is equal to the population standard deviation divided by the square root of n, okay? So now we have to think about what happens here. I want my standard deviation to be cut in half, okay? So what's my standard deviation? It was 3. I want to cut it in half. So that means I want to get my standard deviation reduced down to 1.5. So if I come over here and I look at this, I want my standard deviation, my sampling standard deviation to be 1.5 equals 3 divided by the square root of n. So now my the math algebra skills take over, and we can figure out what n is. Okay, those two things are going to trade places, so we're going to go with 3 and 1.5. This becomes the standard deviation of n is equal to 2, and that means that n has to be 4. So we really don't need a large sample at all to do that. However, what's my issue? I believe this was really skewed to the right, wasn't it? Nope. It's normally distributed to start with. So we were okay with a sample size of 4. If we had reduced the sample standard deviation by half, that would have been something much more significant. It was 160, but we'll stay there. Alrighty, we're going to keep on moving forward. Where are we at here? Oh, only 30 minutes in. We're good. For a population of Leghorn chickens, the mean number of eggs laid is 0.7 with a standard deviation of 0.2. For a population of Sussex chickens, the mean number of eggs is 0.5 and a standard deviation of 10. 2 independent random samples of chickens of size 36 were taken from the populations. The following table shows the sample statistics. All right, describe the sample distribution for the difference in sample means of the breeds of chickens. Leghorn, now tells us Leghorn minus Sussex. So that's nice. No confusion there. So when we describe the distribution, so since it's describing a sampling distribution, really we just have to, context is always helpful. So if we put that in there, we're probably good. But in reality, since it's a sampling distribution, we're just after shape, center, and spread. And if we put a label in there, we've got the context covered, whatever my label might be. So my shape. It's approximate normal because both my samples are over 30. Center. And I realized I just jumped in this problem and started doing it. So I'm going to hold off for 2 minutes here, a minute, and see if you can come up with the center and the shape. Don't need shape twice, do we? Okay, actually, I was started scribbling off my former key and realized that my numbers are all jacked up. So this mean is off a little bit. So let's come back and fix this. Sorry if you already changed that. All right, would that turn out to be 0.0539? What is the approximate difference between the two? What is the probability the difference between the two chickens is going to be greater than 0.3? So it looks like we need to change that problem because this is relatively easy because 0.3 is my. See, I don't know what the heck. I'm looking at, okay, so okay, so we're gonna change this so it's 0.5 because that would be silly and otherwise pointless to leave that at 0.3. And I probably picked I picked a number that's bad as well by picking that 0.5 because it's going to be way, way out there. I don't need it to be way, way out there. So we're gonna change that to a 0.4. Sorry, I'm gonna jerk you around on this a little bit. 1.86 puts us there, which is 96.86. Since the right-hand tail, we're subtracting from 1. And if I can do math in my head today, what's doubting myself, so I'll go ahead and type that in. Yay, we did it. Okay. Let's roll through page 2 of this. Identify the statements are true or false. If false, explain why. So the sampling distribution of both proportions and means are always approximately normal. And this is going to be our false one. And our keyword is always. And it's going to be normal when what? Only when n is sufficiently large. So again, remember we have for proportions, this is going to be n times p is greater than or equal to 10. N times 1 minus p is greater than 10 for proportions. N is greater than 30 for mean. So again, this is one of those things where you just got to start paying attention to, hey, is it a proportion problem? Is it a means problem? It makes a difference. When comparing the sampling distributions of sample proportions for any given sample size n, the standard error 0.8 is less than for point p. Hmm. So again, it's trying to figure out how are you going to go about trying to solve through this. It's kind of like you can talk yourself. It doesn't tell us how big the sample size is because it says for any given sample size. And we kind of got to figure out some way that we can talk our way through this. It's talking about 0.8 versus 0.5. So let's go ahead and see what that is. So if I had one that's 0.5, so I'd have 0.5 times 0.5 divided by n. So that ends up being the square root of 0.25 divided by n. So that ends up being 0.5 divided by the square root of n. Wrong answer. .05. So let's do the same thing and compare that with 0.8. So up here, we're going to have 0.8 times 0.2 divided by n, which is the square root of 0.16 divided by n. And so this is going to be 0.04 divided by the square root of n. So n is going to increase at the same rate. So in one we have 0.04, the other one we have 0.05. So that means that, did we have a true statement or not? The standard error for 0.8 is going to be less than for 0.5, and that will always be true just because of what we just went through here. If we do 0.5, the 0.5, we end up with 0.05 on top. The 0.8, we end up with 0.04 on top. 0.05 is going to be the largest it will ever be, so that means that this is always going to be true. And for any given sample size n, when the sampling distribution of a sample proportion is 0.2 is more skewed than a sample distribution of 0.5. And again, 0.2, that's just going to be one of those cases of true. The further we get from 0.5, the more my variability, the more skewed it can be. So my sample size has to get larger. Excuse me, a certain sin cream is 80% effective or a common rash. A random sample of 100 people with the rash will use the cream. Describe my sampling distribution from a sample size of 100. So this is the same exact thing that we did on the other page, except instead of doing a mean, we had the chicken's mean. Now we're talking about the proportion of skin cream. Okay, so again, we're going to describe the sampling distribution. I'll hopefully step out for a second if I can just keep myself from talking. We have shape, we have center, and we have spread. Our shape is going to be approximately normal, and I'll underline approximately again because we need that word in there. And again, it's a proportion. So that means if we take 100 times 0.8, is that greater than or equal to 10? And then we'll have 100 times its complement of 0.2, and is that greater than or equal to 10? So in this case, we have 80 and 20, both of them being greater than 10, so we are good. Again, trying to get the notation down. We're talking about the mean of my p-hats. Where are we going to expect the mean of the p-hats to be? At 0.8. And we've got the spread of my p-hats. And again, it's an understanding where you're going to find that equation at if you don't start remembering it. Hopefully we'll do enough practice you just start remembering it. What's the probability that more than 85 people will be cured with the skin cream? So what's the likelihood that if I took a random sample of 100, what's the likelihood that 85 of them or more will be cured? And number 6. Suppose that 25% of women and 22% of men would answer yes to a particular question in a simulation. A random sample of 100 women and a random sample of 100 men were selected, and the difference between the sample proportions who answered yes was calculated. The process was repeated 1,000 times. Which of the following is most likely to be representation of the simulated sampling distribution of the difference between the two sample proportions, and explain how you arrive at your answer? Okay, so again, well, this is walking through what we'd expect this to look like. Okay, and we'd expect it to be approximately normal. And why? So we have two groups here. So that means, and we're talking about 25% of women and 22% of men. So that means we have to take, we're going to expect in that group of 125 failures, which is greater than or equal to 10, or excuse me, 25% of the women will say yes. That means that 75% will say no. So that means that if I have a random sample of 100, both of my sample groups are greater than or equal to 10. So that checks out for the women. We have to do the same exact thing for the men coming in at 0.22. So again, both successes and failures end up being greater than or equal to 10. So we're going to expect this distribution to be approximately normal. Which really didn't help me out because all of those distributions are approximately normal. So let's talk about the centers. We're going to have some difference in centers. So let's see what we're going to expect the mean of p hat women. I drew a bar there. We're going to expect that mean to be 0.25 minus 0.22. So that means we're going to talk about a 0.03. So I need a sampling distribution that is centered around roughly 0.03. Okay, so here is 0.03 is right smack dab in the middle of that one. 0.03 is going to fall right about there on that one. 0.03 is going to fall clear back here on this one. So I think we can rule out this guy. And 0.03 is clear the heck down here on this one. So that one's definitely out. So we've ruled out two of them. Okay, as far as their means weren't even in the right spots. So now if we talk about the standard deviation of p hat w minus p hat min, again, we can kind of, it's understanding the formula, where you're going to go for it, square root of my women is going to be 25 times 75 divided by 100. The min is going to be 22 times 78 divided by 100. And so we're going to get a standard deviation of 0.0599. Now, again, it's determining how we're going to use this standard deviation of 0.0599 as far as that goes. So remember, a bell curve is going to be typically 3 standard deviations left and right. So if I have my center located at 0.03, I'm going to go 3 standard deviations to the right and then 3 standard deviations to the left. So for simple math, I'm going to round that up to 0.06. So that means that's going to be 0.03 plus or minus 0.18. So that means I could, if I add those together, I'm going to go to 0.21. If I subtract those, I'm going to get a negative 0.15. So I'm trying to find a scale that goes to negative 0.15 to a positive 0.21. So that means that because of that scale there, my winner is this guy here. Okay. So I'm going to stop my screen share